liar. It's described as an update, and that is true because if you look on our webpage, you will find a similar case study done about 4 years ago, but of course at that time not using the Intel Composer and the Inspector XE and so on tools, but the old ones. And the algorithms got a little bit updated, so this is really in big part new stuff, but based on old material we have done already. Okay, so let's start. Introduction. You know that almost every processor you buy today is a multi-core processor, and you see here in this graphic that we today have almost 99% of the market covered by multi-core processors, so which are this is dual-core and then quad-core and then even more 8-core. In the sessions before, they mentioned that we have released a 10-core system recently. So this is one aspect you need to look at when you write programs today. And then the second one is the ever-increasing data parallelism. So here you see that AVX moved data parallelism from 128 bits to 256 bits in the vector registers, and the Intel Math hardware will offer this for 512 bits. And so even in this dimension we are adding more and more parallelism, and again, to exploit this really you have to do something. A lot of the stuff is done automatically, but especially for threading you need to do some investment. And if you don't do this, you have seen this slide probably from James, you will not get the platform potential, so you get a little bit more. For example, turbo mode is one of the features which you get for free, where you get a performance increase by the additional frequency, but still there is a gap. If you don't do anything for parallelism, then you miss the peak performance of the platform. And I want to show you now how you can use our latest tool suite, the Parallel Studio suite, XE suite, consisting of the Intel Composer, the Intel Inspector for threading and memory checking, and then the performance tool. Levent introduced this yesterday in detail and will do again after my session as another case study. And so another slide is the introduction of the parallel programming models Intel supports. So James covered this in the morning, PBB, Intel Parallel Building Blocks, where we have PBB, the array building blocks, and Cilk. So I don't want to cover everything, but I'll show you in this example code how to use Cilk, and I'll show you how to use alternate key. And it works great on this example, and you see that it's really usable. In general, you have seen this slide probably the years before. The cycle for a perfect program consists of the analysis phase, where you can use the VTune tool, the amplifier tool, to, for example, to understand where in your application you have a hotspot in the original application. And then we have seen this in the presentation before lunch, where they use the VTune tool to see on which parts of their code they have to focus for performance tuning. You shouldn't focus, or you shouldn't try to tune performance where only 1% of your execution time is spent. Then introducing parallelism, for example, by using one of our models, or using automatic parallelization by our compiler. Then debugging, using the Inspector XE tool, for example, for checking for threading issues, race conditions. And we also have this in the Intel debugger for Linux. We don't have this anymore for Windows, but we have a Intel Parallel Debugger plugin for Windows, which extends the Microsoft debugger capabilities for parallel debugging, so for example for OpenMP debugging. And then last but not least, performance tuning. And in this specific session, I want to focus mainly on performance tuning. And so this cycle can be described more specifically in this slide. Typically, we start by a baseline version of the application, which you have already, a legacy application, or you get it, for example, as an open source application for free. You get it from somebody else. It's sometimes a naive implementation, not making use of any optimization. And then, of course, you have the choice to use the Intel compiler, or, for example, the Microsoft compiler here on Windows, GCC on Linux. The next step would be you change the code, and you have some experience, for example, to avoid the recomputation of common sub-expression, or you rearrange code, you move code out of loop, which is loop invariant and stuff like this. And then additionally, you start to introduce vectorization. You want to get two loops executed by data parallelism, by the SSE or AVX. instructions. The next step would be you make use of the multiple cores you have in your hardware. So you start using OpenMP, maybe even native threads like pthreads or Windows threads, or one of the new models like Cilk, in the future array building blocks and so on, or for Fortran, Core Fortran. And then last but not least, you look at our libraries, for example, the Intel Integrated Performance Primitives Library, or the Math Kernel Library, which is very popular, and I'm using it here in my specific code, because MKL offers great features, in particular for these financial applications like the one I'm showing you today. Yeah, coming to this application, this is a computation for the value of options a bank, for example, could emit for a certain stock. And these guys here, they wrote a paper in the 60s, and I think they got a Nobel Prize. They had listed here even. They won a Nobel Prize on this research, and not only for this formula I'm showing you today, but for the whole research they did on how to create mathematical models to compute values of financial assets and so on. And I took a code, or we took a code here from this website. It's financial receipts, I think. So you will get the slides, and then you can go there and look for the original code. Probably looks a little bit different, but the main ideas are the same. And I don't want to go into detail of the financial mathematics here, but it's the basic stuff here. So what we want to do is, we want to compute the value of an option you have today, and we focus on so-called European options, which means you can only exercise this option at the end of the time frame, not in between. This is different from the so-called American option, which you can exercise anytime. This model is much easier than for the American options. We assume no dividends are paid. We assume a certain fixed interest rate. This is important here because if you as an investor decide to put your money into options or into a loan, for example, then of course the interest rate is an important factor, since if you put money into an option, you don't get an interest rate, you don't get money automatically, and so you have to look at alternatives. No transaction fees, and then we assume that the stock price moves really randomly to a higher value or to a lower value. So this is probably not realistic, but of course it makes the model simpler again. So simply this is a random walk of the stock price. It goes up, and at every point in time, it goes up or down, and there is no dependency to the history. So this is what they describe as the geometric Brownian motion. Yeah. And what we are doing here is we compute these options for millions of options for case studies. So this is typically what the financial institutes are doing. They want to play with their parameters, for example, in how much variance they assume in the stock price, or different interest rates, and so on. And there are about 4 or 5 parameters. You will see them in a minute. And so they play with these parameters, and they compute millions of times the value of the call option and the put option, so that they have a good feeling. This is really a realistic example because, for example, a company like Intel, they give options to their employees, and this option has a certain value, but they are not traded. So you don't have a real value in the market, but for example, for your end of year, how do they call this? Balance. You need to know how much value the company has in these options they have given to the employees. So it's really important that they can somehow realistically compute the value of such option, and this is the background of this application I'm showing you. Yeah, this is the mathematics. Don't be afraid. I will not try to explain this to you, and I can't. But it's a solution of a very simple differential equation, and here really there exists a solution, so we don't need to compute this numerically really, and so you get a closed formula. And the formula is listed here, so it involves the cumulative normal distribution. I come to this in a minute. And then you have here these 2 components. You see the logarithm is used, the division, the square root. And so it's a rather expensive formula to compute. Yeah, and the arguments are, you have the initial stock price, or the stock price, the current one. And then you have the exercise price of the option. So to what value you are allowed for a call option to buy this stock later. And then you have the interest rate, and this is the volatility, so how much you assume the stock price will go up or down, so it's a parameter. And then the time in years, for example, until this European option has to be exercised or can be exercised. Yeah, and then this distribution function.